Hey, this is Warp Tech, and I'm here to talk to you about gravity, warp drive, anti-gravity, how it works, why it's already quantized and quantum gravity is a fallacy. Um, yeah, it's really not all that complicated. What you have to think about is that gravity is an entropic force. It's determined by a level of damping. And by damping, I'm referring to the fluctuation dissipation relationship between matter and the vacuum. What they call vacuum fluctuations are also matter fluctuations. Both matter fields and vacuum fields both have a 0 point. And those 0 point fluctuations have an infinite spectrum. And one serves to drive the other and also damp the other. In what we call flat space-time, there's no matter, just vacuum. In a truly flat space-time, what we have is a fluctuation dissipation relationship that is in complete equilibrium. This is not a unique situation. It's unique, yeah, if the only field present is the 0 point field, then it is it would be the same everywhere. Flat space-time would be the same everywhere if it was just the 0 point field. But all the fields from all the matter, like in the entire universe, like you think about Mach's principle, have to be superimposed upon this. And so you can have areas of what would be considered flat space-time that is not the same gravitational potential as another region of flat space-time. So flat space-time itself is not an absolute, but it does have a baseline which would be just the 0 point fields of matter and vacuum. Now, in the region of matter, say we have a gravity well, planet, star, black hole, I don't care. Let's just choose a black hole. Far away from the black hole, let's say the acceleration of gravity toward the black hole is relatively low, similar to that here on Earth. And so the effects of gravity on matter are small. And what this essentially comes down to is the size of the protons and electrons and neutrons and the nuclei and the atoms and the crystals and everything that make up matter is in equilibrium in flat space-time with the vacuum around it. When you start adding other matter nearby, its fields interfere. They don't help. They interfere destructively with the fields from another piece of matter. This interference tends to break the equilibrium. So, as in any other conservative force, equilibrium is broken to results in a force. And so when this symmetry between power into a particle and the power radiated away from a particle into the vacuum is in equilibrium, we have a flat space-time. But when it's falling in free fall, then we no longer have this in equilibrium. We have power in and power out, and they are not balanced. And it is losing energy as the power input drops, or we can think about it as the losses increase. And this is important Think of it as power dissipation. It's resistance. It's the losses in what would normally be a balanced equilibrium that result in gravity. And all we need to do to our quantum wave function is in the exponential terms, the wave function part of the wave, or the wave part of the wave function, we have to add a small damping coefficient. And the damping coefficient results in the Schwarzschild radial solution. It's that simple. Gravity is just a tiny bit of damping added to our wave functions. What that means is, though, gravity is not space-time curvature. Space-time curvature is just an interpretation of what we measure using rulers and clocks that obey quantum mechanics, where atoms and molecules scale according to the amount of damping in the environment. And that's the hardest part of anti-gravity, is getting this interpretation of gravity as space-time curvature, which is not wrong mathematically in any way. It's a wrong interpretation. Einstein's equation has T mu nu on the right-hand side, which is everything we know about physics and thermodynamics and quantum mechanics and quantum field theory. All of that, we already know what T mu nu is. The left-hand side, G mu nu, is called the curvature tensor. And that's fine. Call it whatever you want. But what it really should be interpreted as is the curvature tensor is what we measure when using rulers and clocks that are affected quantum mechanically by damping in the area, in the environment. The bad part about it is much easier to create a gravitational field and cause objects to fall to a region where there's more damping. All we really need to do for damping is agitate the particles, get them to interact more. I can't tell you how to do it. I don't know how to do it. If I knew how to do it, everybody wants to know how to verify my model. My model predicts everything general relativity predicts. How do you verify general relativity? It's the same thing with a different interpretation. Now, if you want an experiment for anti-gravity, it's no easier understanding it quantum mechanically. You need to essentially cause subatomic particles, atoms, molecules to inflate. The opposite of length contraction. You need them to oscillate faster, the opposite of time dilation. When Jack Sarfati talks about the blue shift. That's correct. That's the right way to think about it. Everything has to be blue shifted and expanded. Hal Puthoff talks about the energy field that's created. That's right. When you take matter and inflate it, its energy state is higher. Therefore, it's more resistant, like a shield. It's more resistant to hitting things at warp speed. But making every subatomic particle on the ship inflate simultaneously at scale, tuned together so that matter is not torn apart when this happens, is an enormous amount of energy, no matter how you slice it. Whether you use general relativity to figure out what the energy requirements of warp drive are, or you use quantum mechanics, the energy requirements are enormous. Now, it's not the energy of the entire sun or the galaxy or the Earth. They are feasible, but not in a garage or on a lab bench. It's just not. Avogadro's number is a huge number, and increasing the ground state energy of every subatomic particle in a sample is a huge number. If you wanted to cause anti-gravity, it is a subatomic effect that has to take place at that scale to not just eliminate damping, but to amplify the driving forces, the fluctuations. You would need to amplify the 0-point field, amplify the fluctuations beyond what they are in flat space-time 0-point field. Literally, the way to warp between point A and point B is not to bring these 2 points closer together, which is impossible. It is to increase the length of your ship so that in your frame of reference, the distance between them is shorter. But that means relative to their frame of reference, in your frame of reference, your ship, your warp ship is stretched, inflated. If you want 300 times the speed of light, you're going to be 300 times longer than you are naturally. But if everything is scaled uniformly, all forces remain the same. The force doesn't change. So interacting in this environment is normal. You wouldn't know. Just like you really can't tell the difference between standing on the ground or if you're in an airplane or in a space capsule. The change isn't that great. But because the change in the speed of light is not that great. But when you want to go 300 times the speed of light, the change is enormous. I'm not saying it's impossible. I'm just saying it's not an easy thing to do. Any field that is RF based or microwave based or anything like that, the skin depth will never allow it to penetrate the ions and nuclei and protons and neutrons in every atom inside everything to be transported. It's just not going to work that way. About the only ideas I have are sound, because sound actually causes all the particles to vibrate. But how does that make a warp drive? I don't know. Anyway, these are some ideas going through my head. I hope you all enjoyed it. Take care.